if we had the following system of equations, so we've got x plus 2y equals 8, and 3x plus 4y equals 9. We've got two equations and two unknowns. And we say that these are linear equations because there's no x squared, there's no y squared, there's no x times y, and there's no like sine or cosine or e to the x or anything like that. So these are linear equations. And if you have two linear equations with two unknowns, it's pretty easy to solve. You know, what we could do here is I could say, let's take my second equation and subtract 3 times my first equation. And then 3x minus 3x is 0. 4y minus 3 times 2y is 4y minus 6y, that's minus 2y. And then 9 minus 3 times 8 is 9 minus 24. And 9 minus 24 is negative 15. And so then we know that y is 15 over 2. And if y is 15 over 2, you can just plug that into anything, right? So we can say x plus 15 equals 8. So that means x is equal to like negative 7. Okay. So now we know what x is, we know what y is, and those values of x and y satisfy both equations at the same time. There's another way we can do things which is exactly the same as what we just did, but we're going to save a little bit of time just by not writing x and not writing y and not writing plus and not writing equals. The way we're going to do this is with Gaussian elimination. And I'll show you exactly what that looks like. We're going to write this. And this is what we call our augmented matrix. This augmented matrix represents that system of equations. So what I did is I ordered my equations so that I have my x term plus my y term equals my constants. And then you just write down what the coefficients are, like 1, 2, 8, and then 3, 4, 9 represents, each row represents an equation. And so then, if I want to solve this, my goal here is to eventually rewrite this augmented matrix like this, where there's ones on what we call the diagonal, there's zeros in what we'd call the off-diagonal entries, and then the final column is going to contain my values for x and y. But there's only certain things that we're allowed to do, because you can remember that like each row here, each row represents an equation, so like I can add and subtract those, just like I could add and subtract equations, but I can't I can't just do anything I want. You know what I mean? Like I can't break the rules of algebra. You always have to remember in your head that these represent equations. Rows represent equations. So one thing I could do to start off is I could say, let me take the second row minus 3 times the first row. And that's what we did a moment ago, but with the whole equation. And so if the second row is going to be the same thing minus 3 times the first row, then the second row is going to be 0. 4 minus 3 times 2 is negative 2. And 9 minus 3 times 8 is negative 15. And then the first row remains the same for right now. Then the second row is representing the equation 0x minus 2y equals negative 15. But maybe I want to multiply the second row by a negative 2. And I could multiply a whole equation by negative 2. Or I could say divide by negative 2. What I really want to do, I want to divide the second row by negative 2. And it's the same thing as dividing an entire equation, left side and right side, by negative 2. So that's allowed. And 0 divided by negative 2 is 0, negative 2 divided by negative 2 is 1, and then, of course, negative 15 divided by negative 2 is 15 over 2. And then maybe the last thing I'll do is I will subtract 2 times the second row from the first row. So I'll take first row minus 2 times the second row. And 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0. 8 minus 2 times 15 halves is 8 minus 15, and that's negative 7. And then the second row remains exactly the same. And now, remember the rows represent the equations. So the first row represents the equation 1x plus 0y equals negative 7, and then the second row here represents the equation 0x plus 1y equals 15 over 2. So we did exactly the same thing we did before, but we're just saving time by not writing the variables and not writing the plus signs and not writing the equal signs. And so we call this Gaussian elimination. It's also called row reduction. Like if you're looking on like Khan Academy, they might call it row reduction. I don't remember what it is called in Khan Academy. But then of course the zeros don't matter. And you just find that x is equal to negative 7 and y is equal to 15 over 2. So that's the goal of what we're doing here. So the allowed row operations, there's 3 of them. You can subtract or add, I should say add or subtract. You can add or subtract one row from another row, just like you can add or subtract equations when you have a system of linear equations. The next allowed row operation is that you can multiply any row by a constant number, or divide, like we divided by negative 2. So then you can multiply or divide one row by a scalar, just a number. It's really important to say this, but like you can't multiply 2 rows. Like you can't say I'm going to take row 1 times row 2. That doesn't work because you can't multiply equations like that. You can only add or subtract rows, and you can only multiply or divide a row by a scalar. You also can't like subtract a scalar from a row. You know what I mean? Like you couldn't go back here and say, let me just add 3 to every element in the second row. That's not something you could do with an equation, so it's also not something you can do with a row. The last thing that you are allowed to do, there's only 3 things you're allowed to do. The last thing is you're allowed to swap the position of the rows. Because again, in a system of equations, it doesn't matter which equation you write first and which equation you write second. So when it comes to the rows in an augmented matrix, you can also just swap the position of the rows if you want to. And so these are the only 3 allowed row operations. The question is, can you swap columns? And the answer is yes, you could swap the columns, but remember that our columns were representing the coefficient on x, the coefficient on y, and the constants. So the answer is yes, but not the last column, because you always want the last column to be your constant. And if you choose to swap the columns like the x's and the y's, you have to keep track of the order of your variables. So like if I were to choose to swap the first column and the second column, change their position, so that now the second column is the first column is the second column, that means that when I'm done with Gaussian elimination, the final column, instead of having the values of my variable x and y, it'll then have the value of my variables y and then x. So you swapped the order of the columns, you're going to swap the order that your solution appears. Okay. Otherwise, yes, you can swap columns. I don't normally do that. I don't normally recommend that because you have to keep track of the order, and that's a whole separate thing. Okay, so here's a practical example of where you might want to use this. Suppose that you wanted to make yourself like a smoothie. You're like a fitness nut. Maybe you want to, track your macros and whatever. You've got certain health goals. You say, I want to make a smoothie for breakfast, and the only ingredients that I want to use are oats and peas and coconut. And maybe you decided this because, I don't know, maybe you're like a vegan, and maybe you know that oats are a really healthy source of carbs, and peas, that's a pretty healthy source of protein, and coconut is a really healthy source of fat. And so if you're, in terms of tracking your macronutrients, you should be able to find a blend of these ingredients that gets you exactly the right balance of carbs, protein, and fat that you're trying to aim for. So let's say we're trying to make a smoothie with this 52 grams of carbs, 35 grams of protein, and 23 grams of fat. I don't actually know if that's a healthy smoothie, but let's say that was your goal. Okay? And you happen to know that for 10 grams of oats, peas, and coconut, you have these, this breakdown of carbs, proteins, and fats. So then what is the recipe for your smoothie? A recipe would just be how much oats are we going to add, how much peas are we going to add, and how much coconut are we going to add. So we can write a system of equations. We're going to say that X represents 10 grams of oats, Y represents 10 grams of peas, and Z represents 10 grams of coconut. And then I'll write this system of equations. We're going to say that 7x plus 3y plus 4z is equal to what? 52. Why is it 52, Blake?
This is carbohydrates.
Yeah, that's my carbohydrates. I get 7 carbs for every 10 grams of oats, 3 carbs for every 10 grams of peas, and then 4 carbs for every 10 grams of coconut. So if I add that together, I should get my 52, my target amount of carbs that I want. Okay, the next equation is going to be 2x plus 6y plus 1z is equal to 35. Yeah, that's my protein target. And then 1x plus 1y plus 5z is equal to 23 because that's my fat target. So now this is a system of equations where I've got 3 equations and 3 unknown variables. And if I just solve these for x, y, and z, I'll know exactly how much oats and peas and coconut you want to add to your smoothie to hit exactly those carb, protein, and fat targets. Okay? So, what my goal here, I'll try to explicitly define what I'm trying to get to. My goal here is that the diagonal should just be 1s, and then whenever I get a diagonal of 1s, and all of the off-diagonal entries as 0s, then the final column of my augmented matrix at that point should just have the values of x, y, and z. Okay? And with that goal in mind, we're going to go ahead and write the augmented matrix for this system. So my augmented matrix is going to look like 7, 3, 4, 52. 2, 6, 1, 35, and 1, 1, 5, 23. Now I want that 7 to be a 1. And to make that 7 into a 1, I'm going to subtract 3 times the second row from the first row. Because if I subtract 3 times 2 from 7, it'll make it a 1. And so let's imagine we do that. 7 minus 3 times 2 is 1. 3 minus 3 times 6 is negative 15. 4 minus 3 times 1 is 1. And 52 minus 3 times 35 is 52 minus 105, which is it negative 53? I don't know for sure. The next thing I need to do is I want to make this 2 into a 0. So I'm going to subtract 2 times the third row from the second row. So 2 minus 2 times 1 is 0. 6 minus 2 times 1 is 4. 1 minus 2 times 5 is negative 9. 35 minus 2 times 23 is going to be 35 minus 46. And that's negative 11. And the last thing that I'm thinking about is I want that 1 right here in the bottom left corner. I want that 1 to be a 0 in the end. And so I think I'll subtract, I'll take the third row minus my new first row. Right, so it'll be like this equation represented by this row minus that equation represented by that row. So 1 minus 1 is 0. 1 minus negative 15 is going to be 1 plus 15. Yeah. 5 minus 1 is 4. And 23 minus negative 53 is going to be 76. Yeah. Yeah, please stop me if I make a mistake, because there's so much adding and subtracting and multiplying. It's very easy to make a mistake here. Okay. The next thing that I'm thinking about here is making this 4 into a 1, but I can't think of an easy way to do that, so we're going to forget about that goal for right now, and then we'll move on to making the 16 into a 0. To make that 16 into a 0, yeah, so I'll subtract 4 times the second row from the third row. That's a good idea. So just third row minus 4 times the first row. 0 minus 4 times 0 is 0. 16 minus 4 times 4 is 0. 4 minus 4 times negative 9 is 40. 76 minus 4 times negative 11 is going to be 76 plus 44 is 120? 120? Okay, cool.
Oh, cool. Divide that by 40.
Yeah, and we'll leave everything else the same for right now. Yeah. We'll just leave that alone. Sometimes trying to do too many steps at once gets you in trouble, so. Things are turning out pretty well. I'm running out of space, and so I'll circle back up, I guess. You can remember what our goal is. Yeah, what I'll do next is we'll make this third row just the same third row divided by 40. So right now this equation is telling me 40z equals 120, but that's the same thing as 1z equals 3. Okay, so divide the third row by 40, and we get a 1 there and a 3 there. Okay, I want this negative 9 to be a 0. So let's add 9 times the third row back to the second row. And so my new second row is going to be 0 plus 9 times 0, 4 plus 9 times 0, negative 9 plus 9 times 1 is 0. And then negative 11 plus 9 times 3, right, is 16. Okay. Again, I could also look at the second row now and just divide it by 4. So let's divide the whole new second row by 4. Instead of 4y equals 16, it will represent 1y is equal to 4. And we might even be able to finish this up. No, we're not going to finish it up in this step. We're close, though. So let's just call the first row 1, negative 15, 1, negative 53. There'll be like 2 more steps before we're done here. Okay, so going around here. We already have the third row and the second row looking exactly how we want them to look. Now to make the negative 15 go away, I'm going to add 15 times the second row to the first row. So that will be 1, 0, 1, and what's 15 times 4? 60. Negative 53 plus 60 is 7. And then you can imagine we're almost there. We just have that pesky 1. So let's subtract the third row from the first row. And subtracting the third row from the first row, this is going to be a 0, and that's going to be a 4. Okay. So now this final column represents the values of x, y, and z that satisfies this system of equations. And that means that to make my perfect smoothie, I want to add 40 grams of oats to 40 grams of peas and 30 grams of coconut. I don't know if that would actually be palatable, but that's the idea. And this is kind of an interesting, like, real-world problem because there's companies that do this. You know, there's companies that make health shakes and sell them to people as, like, ground-up powders of different vegetables and whatever. And they want to hit certain macronutrient targets so that they can sell their product. And so they actually probably do have somebody that sits and doesn't solve this by hand. There's ways you can do this with a computer that doesn't involve solving it by hand. But this is how it works. Okay, so maybe you've heard of this, maybe you haven't. The next thing I want to just briefly mention is round-off error. Because anytime we do something on a computer is just a machine that knows how to add and subtract things. But computers have a finite memory. They have a finite storage ability for numbers, right? So if you have the number pi, some of you might be aware that, like, pi has an infinite decimal expansion. If you try to represent pi as a decimal, it just keeps going and going and going, and there's never any sort of pattern, nothing ever repeats. It's just an irrational number. So computers cannot store irrational numbers in their memory. Computers can only store numbers represented by a finite number of possibilities. It's huge. You know, it's a huge number of possibilities. If you were to use 64 bits, you know, like zeros or ones, then every bit can represent either a 0 or a 1, so there's 2 possibilities. I think a common system is like using like 64 bits to represent like an integer. So it's like how many different integers could you represent in, you know, a long format would be 2 to the 64, which is a huge number. So like computers are pretty darn precise, and you can get as much precision as you want basically by just using more and more bits to store a number. But it's still limited. There's still a limited precision whenever you use a computer. And I'll give you a demonstration here in Microsoft Excel. If I type in equals 1.005 minus 1, what should the result be? What should I get as my answer? 0.005, right? Okay. So if I ask Excel to represent this, with this many sig figs, Excel thinks that 1.005 minus 1 is the number 0.00499999999999989. Right? And the reason for this is that, like, as the computer is performing the subtraction algorithm, it introduces round-off errors as it goes, and it ends up settling on, you know, a number in its floating point number system that's close to, but not exactly the number that we want from subtraction. So these round-off errors are really, really, really tiny. Notice, like, we're really close to the number 0.005. But they happen every single time you do some, like, kind of addition, subtraction, multiplication, division. And so whenever you start to program to answer math problems, you have to keep this in mind, that sometimes your algorithm might introduce a lot of round-off error. So normally not an issue, but a lot of times in, like, computational applied math, you end up with, like, really big problems. Like, if you were trying to work on, like, a fluid simulator, you might have a situation where you have, like, 100,000 linear equations with 100,000 unknowns. And so you want to do, like, a Gaussian elimination algorithm. You want to write a program that will perform what we just did, but on a huge, huge, huge system. And then you feed that program to a supercomputer, and you let it chug all the numbers for you, so you don't have to sit there and do it by hand. But the problem is, with that much adding and subtracting and multiplying and dividing, you can start to introduce significant round-off errors. And so basically, the Gaussian elimination algorithm that's used in practice looks something like this. You know, we've got some matrix. I'll write a 3 by 3 because we just worked on one. It's easy for me to try to take this strategy where I start here, and then I do this, and then I do this, and I'm trying to make it 1, 0, 0, and then I try to make that a 1, and then this is 0, and then this a 1, and then this is 0, and then that is 0, and then that is 0. That's normally the route that I take. So, like, as a little roadmap, it looks like this. Computers do mostly the same thing, except every time a computer moves down from, like, the first row to the second row to the third row, what it does is it looks for the largest entry in the submatrix, the lower right submatrix, and then it row swaps and column swaps until the largest entry is the pivot. It's on the diagonal of the row that you're trying to work on. And then it makes that a 1 and all of the entries below that into zeros, and then it moves on to the next row and it row swaps and column swaps so that the largest entry is on the pivot, and then it does it and it goes like that. So that's actually the best algorithm for minimizing round-off error. It's not something you have to know, but I think it's interesting that, like, there's a whole field of math where people study that and think about that, like, how do you do math on machines, on real-world machines. If you're really interested, you could take a course when you transfer to a university in applied or numerical analysis is where you learn stuff like that. In Python, we can go to Anaconda Navigator and then launch Spider. We can do this really, really, really easily. Can everybody see this pretty well? Can you turn off the lights maybe? Maybe that's going to make it show up a little better. Actually, I can probably also zoom in.
All of them are just like that? That's fine.
That's probably fine. Let me see if there's something I can do to make the text a little bit larger. We'll make all the text 16 point. There we go. Okay. So, is everybody at this point on your laptop, if you have one? No?
No.
Okay. Well, so I'm taking a screen recording of this, and this microphone is capturing all my commentary, so you could watch this later and then catch up to do your project. Okay, so the first thing we're going to do is we're going to type import NumPy. NumPy is what we call a library in Python. And actually, before we do that, well, let me just show you something. If I try to type in sine of 0, Python tells me that sine is not defined, okay? So Python does not know what the sine function is by default. But what NumPy is it's a library. And if I ask Python to import all of the functions from the NumPy library, you do this by typing from NumPy import star. Star just means everything. Now Python knows all of the commands that are in the NumPy library. So now I can ask things like sine of 0. It'll tell me sine of 0 is 0, and of course cosine of 0 is 1, and things like that. So the NumPy library stands for numeric Python, and it contains math functions that we need, like sine and cosine and all that stuff. Okay. So we've imported NumPy. The next thing I want to do is I'll define a little matrix. We'll call it capital A. And the first row of the matrix should be how many carbs is in 10 grams of oats? Was it 7?
52.
We were aiming for 52. That was our goal.
It was 7.
7?
Yeah.
Okay. How many grams of protein were in 10 grams of oats? So it was probably 2 and then 1, and then we were shooting for 52 carbs. So that's the first row of my matrix. I did bracket, bracket, and then the first row. I'm going to do comma, bracket again, and this is going to be the second row. So now we're thinking about peas. How many carbs are in peas? Was it 4? Oh, nobody has their notes.
The 3, 6, 1, 35.
Let me pull it up. We'll make sure we got the same answer we did by hand.
Computer didn't crash.
Okay. We said 2, 6, 1. Although that doesn't really add up to 10 grams, does it? It was supposed to be 3, 6, 1. I just wrote it down wrong. So we'll say 2, 6, 1 because that's actually the problem that we solved was 2, 6, 1. 2, 6, 1. And we were shooting for 35 grams of protein. And then my last row was like 1, 1, 5 maybe? 1, 1, 5. Oh, sorry. These rows aren't by oats and peas and coconut. These rows are actually by carbs and proteins and fat. So it should be 3, 7, 4. No, 7, 3, 4. I'm sorry. We're doing rows of the matrix. So 7, 3, 4. 2, 6, 1. I got it confused. We're doing this right now. 1, 1, 5. And then 23. Okay. So everybody agrees. This is the matrix, the augmented matrix, where I wrote each of my rows in square brackets. And then I wrote all those things together in another set of square brackets that goes around the end. And so I just told Python what my matrix looks like, and now if I type in A, Python will tell me again, hey, this is what your matrix looks like, okay? Then what we're going to do is type in linalg.solve, and we're going to type in A, comma, hold on. I'm trying to think. I didn't do this right. Okay, sorry. We're going to try this again. This time we're going to leave off the last column. (52, 35, 23). That's going to be my new matrix. And then we're going to define a vector b, and old b vector is going to be 52, 35, 23. There we go. So I've got a matrix A, I've got a vector b. Now I want to do linalg dot solve a comma b. And the solution that Python came up with was 443, which is exactly the same solution that we got whenever we solved this by hand, just with our row reduction techniques. So what's actually happening here is whenever I type in linalg.solve, this stands for linear algebra.solve, what Python is doing is it's taking my matrix A and it's augmenting it with the vector B so that we have the full augmented matrix. And then it's doing Gaussian elimination, and it sees what it gets at the end, and that's what it tells you is the solution. It's 443. So now you know how it works. Now if we use this command, it's easy in Python. You just have to type in solve, and it does it for you. But now at least you know how it works and what's happening in the background. Okay. So a little bit more math notes. I don't remember how much I've actually said about this stuff in class, so we'll just go over it. Every time we use the word matrix, we're talking about a rectangular array of numbers as rows and columns. So like these are all matrices. Whenever we talk about the size of a matrix, we have to use two numbers. We talk about the number of rows by the number of columns. So this is a 2 by 2 matrix. This would be like a 4 by 4 matrix. And since we always use rows first, this would be like a 3 by 2 matrix because it's 3 rows by 2 columns. So whenever we talk about the size of a matrix, it's rows by columns. Okay, if we have a matrix like this one, in my little example, if we've got this matrix A, then we always identify the entries with a row number and a column number. So like lowercase a 1 comma 2, that is going to be referring to the first row, second column. So that's 6. If I ask you for a 2 comma 1, that's talking about the second row, first column. So that must be 7. If I write a with subscript 1, I'm talking about the first row, which is 5, 6. And if I were to use this notation, where the subscript is colon, comma, 1, this is talking about the first column. And that's kind of weird. But what that 1 is telling you is it's saying first row, because we always use row first, row comma column index. What the colon is telling you is like everything from that row in the first column. No, sorry, I misspoke. It's saying all of the rows. Whenever you say the colon for the row index, it's saying all of the rows, comma, first column. So Python uses a similar Python uses a similar notation that I use. So like what I just said, a equals 0, open parentheses, square bracket 2 comma 2, square bracket parentheses. What this did is it just reset the variable a so that it represents a matrix with 2 rows and 2 columns where all the entries are zeros. So I could make the B matrix just a matrix full of zeros with 3 rows and 5 columns. Right? We always do row, comma, columns. And so now it looks like that. 3 rows, 5 columns, and it's all zeros. Okay. Back to my matrix A. Let's say the matrix is 5, 6, 7, 8 for the entries. I can assign the values of the entries by doing this. Except maybe the difference is we normally talk about this as being the first row, first column. But for Python, Python numbers stuff starting with the 0. So for Python, this is the 0th row and the first row, and the 0th column and the first column. And so if you type in A00 with the square brackets, it's telling you the row index and then the column index. And so if I tell Python that the 0th row, 0th column is equal to 5, it's going to put a 5 in the top left. And then likewise, if I want to put a 6 in the top right corner, I would say 0, row number 0 and column number 1, that has to be equal to 6. And so now I'll put a 6 in the first row, second column, because again, we're starting our indexing from 0. And then if I assign a 7 to the bottom left, that's how I do that. And then lastly, if I want to assign an 8 to the bottom right, I do that. Okay. So I've got that matrix. If I ask Python for just one, I only use one index, it's going to assume that's the row index. And so it should give me an array that's just 5, 6. Oh, sorry, I forgot we start our index with 0, right? So if I put in 1, it's going to give me the second row. It's going to give me 7, 8. So let's try A0. 5, 6, yeah, that's the first row. Okay, now what if I do colon, comma, 0? That should give me the first column, 5, 7. So the colon is telling you, give me all of the rows, only the first column, or column number 0. And so then I can do this to get the second column. All right, so that's tricky. It's hard to get your mind around. But anyways, here we go. Matrix vector multiplication is defined like this. If I have, let's say, a matrix A, and let me just define a new matrix. That's a 3 by 3 matrix where it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's say I have a vector V, and V is, maybe the vector 0.4, 0.7, negative 0.1, or something like that. If I want to take the matrix vector multiplication, like A times V, what the product is going to be is a vector where notice the first entry in the product vector is the first row of my A matrix, dot product the V vector. So the first entry here is going to be 1 times 0.4 plus 2 times 0.7 plus 3 times negative 0.1. And that's just one entry in a vector. The second entry of the vector is going to be 4 times 0.4 plus 5 times 0.7 plus 6 times negative 0.1. And you can guess what the third entry is going to be. But you take the dot product between the rows of the matrix and the vector. And each one of those dot products becomes an entry in the product vector. So we always write the matrix A on the left and the vector V on the right. The product is going to be a vector. And I already kind of explained how to compute this. Let's do one of the easier examples that I typed out here. Like if I have the matrix M being this one, 1, 1, 0, 1, and U is 3 and 4, M times U is going to be a vector where the entries are 1 times 3 plus 1 times 4, and then 0 times 3 plus 1 times 4. Just the dot product of the rows of M with the vector U. And then, of course, this is going to be 7, 4. That's the matrix vector product. Okay, what about this one? I've got a matrix N times a vector A. And the product is going to be a vector where the entries are the dot product, so it's going to be 1 times 4 plus 0 times negative 3 plus 0 times negative 1. And then 1 times 4 plus 2 times negative 3 plus 0 times negative 1. And last entry will be 1 times 4 plus 2 times negative 3 plus 3 times negative 1. So again, my matrix vector product will be a vector where the entries are 4, negative 2, and negative 5. I guess it's never hurts to just do more examples. So if I have matrix B and vector V, their product is going to be a vector. This time there is only going to be 2 entries because there's only 2 rows of my matrix. And we take the dot product 4, 5, 6 and 1, 1, negative 1. So it'll be 4 times 1 plus 5 times 1 plus 6 times negative 1. And then second entry, negative 4 times 1 plus negative 5 times 1 plus negative 6 times negative 1. And that is going to be 3. And negative 3, I think. Yeah, that makes sense because the first row and the second row are just the opposite. So that's going to be the matrix vector product. Okay, do you have questions about how a matrix vector product is found?
No. But you'll never have like a vector that doesn't equal the columns.
Ah, great question. Great question. So, in matrix vector multiplication, this is something you need to write down in your notes.
Okay.
This must be true. And Blake was just asking about this. So, excellent question. The number of rows in your matrix has to be equal. Oh, shoot. I lied.
Isn't that
That's
columns?
columns. Yeah. My bad. I think I found that as a typo last spring and I forgot to change it in my notes. So this should be columns. The number of columns in the matrix has to be equal to the number of entries in your vector. If you have a mismatch, then you won't be able to do the dot product, right? Every entry in the product vector is a dot product between the row of the matrix and the column and the vector. And the only way to take a dot product is if you've got the same number of entries. So this always has to be true. If it's not true, then you can't do matrix vector multiplication. And the other thing that maybe you notice is that in matrix vector multiplication, the product vector has the same number of entries as the number of rows of the matrix. So if your matrix that you're multiplying has 2 rows, then your product vector is going to have 2 entries. Does that make sense? Okay. Okay, so what a matrix vector equation is then is you've got some matrix A times some vector X, and that is equal to some vector B, right? So matrices are going to be capital letters, vectors are going to be lowercase letters in my notes. If you happen to know A and X, then to solve for B in this equation, you just have to do matrix vector multiplication to find your B vector. B is just your product vector from matrix vector multiplication. If you happen to know A and B, you can solve for X by using Gaussian elimination. Let me kind of explain that a little bit. If I have a matrix A, which is just 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's say that my X vector is equal to the vector, let's say, M, N, now let me name it something different. Sorry for changing the variable names on you. But let's say we have the equation AV equals B. And let's say that A and B are known quantities. But V is unknown. Right? So we want to find what is my vector V. Since I don't know what these entries in my vector V are, let's call them X, Y, and Z. And these are equal to some known vector B. So let's come up with some numbers for B. It could be anything, but let's call it like 1, 0, -1, just for coming up with an example, you know. So, what would matrix vector multiplication look like? On the left side of my equation, this matrix vector multiplication would be a vector product that has 3 entries. And the 3 entries are the dot product between the rows of A and the vector x, y, z. So in other words, it would be 1x plus 2y plus 3z. The second entry would be 4x plus 5y plus 6z. And the last entry would be 7x plus 8y plus 8z. And I put 7, 8, 8 for some reason. And my equation is telling me that this is supposed to be equal to 1, 0, -1. But if this vector has to be equal to that vector, this is the same thing as having a system of 3 equations, 3 linear equations with 3 unknowns. And how did we solve for x, y, and z when we had a system of 3 linear equations with 3 unknowns? We used Gaussian elimination. And so if you use Gaussian elimination on this system, we could find x, y, and z. And again, that's what we were trying to find. We were trying to find what is this vector v in my matrix vector equation. And so again, what I put here in my notes is that if you happen to know what is the matrix A in the vector B, then solving for your unknown vector V, that has to require Gaussian elimination. So we call these matrix vector equations, and they're pretty important. They show up all over the place. if you want to do matrix vector multiplication in Python, it's not so hard. This is my matrix A. Let's come up with a vector V. We'll call it the vector 15, 30. Make it 35 just to make it a little, I don't know if it's important or not, but okay. So here's my matrix, 2 by 2 matrix. Here's my vector, 2 entries of my vector. If I want to multiply these, I think the command is matmul, and I do A comma V. And so the product vector, A times V, is going to be the vector 285, 385. Okay. Not so bad in Python anyways.
Quick question. How are we gonna how do we know what commands to use? Is there like a list, or you just got this?
Good question. So you can either watch this video whenever I post it and make it available to everybody to watch, or you can look up Python NumPy, just for example, matrix inverse. Just Google search this. And there's all sorts of sources that will try to teach you Python on the internet, but numpy.org has documentation for what commands exist in their library, and you can click, and there will be a little article that it's kind of weird. I don't know why that has to go to bean.com first. But anyways, this right here, that would be the command, is linalg.inv is how you'd find the matrix inverse. And it will also suggest a bunch of, related commands that you might want to use if you're working in NumPy. But NumPy is a huge library. It's got hundreds of commands. And so anything you want to do, just Google search it, Python NumPy, and then the thing that you're trying to do. You can find the command. As a quick refresher. Okay, so we figured out how to do matrix vector multiplication. Now we can do matrix multiplication. So if A and B are both matrices, then this is how you would multiply 2 matrices. Whenever you have, that should be matrix multiplication. I've got lots of typos. With matrix multiplication, the product is going to be a matrix. So you multiply 2 matrices, the product is a matrix. The columns in the product matrix are going to be the matrix vector products of the left matrix. In this case, it would be A, and the columns of the right matrix. In this case, it would be B. So A times B means take the matrix vector product of A with each column of B. The matrix vector product is going to be a vector, and each of those vectors are going to form the columns of the product matrix. In general, if you've just got 2 old matrices sitting around, matrix A and matrix B, the product is not going to be commutative. So A times B is normally not the same matrix as B times A. It's kind of weird because with numbers, multiplication is commutative. 5 times 3 is 15 and 3 times 5 is 15. That's not how it works if you're multiplying 2 matrices. So it really does matter which one is on the left and which one's on the right. So I'll try to make up a quick example. These problems can sometimes take a long time. So let's say the matrix A is the matrix 1, 1, 0, 1, and the matrix B is the matrix 1, 2, 3, 4. then A times B is going to be the matrix where the first column is going to be the matrix A times the vector 1, 3, and the second column is going to be the matrix A times the vector 2, 4. So in the upper left corner, the first entry is going to be 1 times 1 plus 1 times 3. The upper right corner entry is going to be 1 times 2 plus 2 times 4. The bottom left entry is going to be 0 times 1 plus 1 times 3. And then the bottom right entry is going to be 0 times 2 plus 1 times 4. There's actually a specific way I like to think about this, and maybe this makes sense to you. If it makes sense, that's great. I hope so, because it'd be reassuring to me that I'm not like going crazy. I like to write the left matrix on the left and the right matrix like slightly up, like this. And then the product matrix I put in the little corner right here. And to calculate this entry, you're going to take the dot product of this and this. And to calculate this entry, I don't know if that color is different enough. This entry, you're going to take the dot product of this column and that row. And if you want this entry, we take the dot product of this column and this row. And then last thing is choose a nice purple, I guess. If I want that entry, I take the dot product of that column with that row. Does that help? Or is that just as confusing? So, for example, bottom right entry should be 0 times 2 plus 1 times 4. The yellow entry should be 1 times 2 plus 1 times 4. And yeah. Okay. So the great news is that we don't actually have to like do this by hand. I want you to know how it works because theoretical understanding is important. But let's say that the matrix A is the matrix 1, 1, 1, 0. The matrix B is that matrix 1, 2, 3, 4. That's how I tell Python what A and B are. And then if I want their product, I just have to tell Python matmul for matrix multiplication, A comma B, and then it will tell me what their matrix product is, right? So that's why computers are good. It should be 4, 6, 1, 2, which is 4, 6. Did I make a little mistake? 1, 0, 1. My matrix A is slightly different, but whatever. I'm not going to worry about it. Important in matrix multiplication, the number of columns in the left matrix has to be equal. Did I mess this up? Hold on, let me think. No, this is actually correct. Okay, so the number of columns in the left matrix has to be equal to the number of rows in the right matrix. This must be true, or it doesn't work. Like, you can't do matrix-matrix multiplication unless this is true. Again, the reason is because every single matrix in the product matrix, every single entry in the product matrix is a dot product. And for you to be able to take that dot product, the two vectors have to have the same number of entries, and so the number of columns in the left matrix has to be equal to the number of rows in the right matrix. Otherwise, it doesn't work. So let's say we have A times B equals C. So A is going to have a certain size. It's going to have a certain number of rows by a certain number of columns. B is going to have a certain size. It's going to have a certain number of rows times a certain number of columns. Then C has to have the size with the same number of rows as A had and the same number of columns that B had. Those will be the size, that will be the size of your product matrix. And then what I'm saying here in purple is, furthermore, if this multiplication is going to happen at all, the number of columns of A has to be equal to the number of rows of B. Does this make any sense? You're tracking. Okay. So this is easy. A square matrix is exactly what you think it is. If the number of rows is equal to the number of columns, then we call it a square matrix. So 2 by 2 matrices are square, 3 by 3 matrices are square, 4 by 10 matrices are not square. Okay, the identity matrix is any matrix with ones on the diagonal and zeros off the diagonal. So an identity matrix might look like this. And hopefully you can see what I mean by the diagonal. The diagonal is always the set of entries that have the same row and column index. So with row index 0, 0, 1, 1, 2, 2, and 3, 3, those entries should have the value positive 1, and all of the other entries should be zeros. That is what we would call the 4 by 4 identity matrix, but you can come up with any identity matrix for any square dimension. So there's a 3 by 3 identity matrix, a 4 by 4, a 2 by 2, a 5 by 5, you know. Identity matrices have to be square, but other than that, they can show up in any size. We also have a notation for this. We call it capital I for identity. And if you want to make an identity matrix in Python, there's a really easy way to do so. You just tell it the size of identity matrix you want, and you use the command I spelled out EYE. I don't know why. I guess just phonetically that makes sense. And so if I type in capital I equals I, the identity matrix with size 4, now Python has the variable capital I mapped to this matrix where there's ones on the diagonal. Good?
That only work for square matrix, or is that for any other one as well?
So identity matrices have to be square.
Okay, so because you put 4, so I don't know if it was doing like 4 across or for the row.
That's going to do 4 rows and 4 columns.
Okay.
Mm-hmm. Yep. Yeah, so the matrix A right now, or let's use B. No, that's lowercase b, capital B. Okay, so the matrix capital B right now is the matrix 1, 2, 3, 4. let's now set the capital I equal to the identity matrix with size 2. So now that's the capital I matrix. What if we do matrix multiplication of I times B? It's going to give me the same matrix as the B matrix. So it's just like the number 1 is the identity for multiplying numbers. Like 1 times 5 is 5. Well, any identity matrix times any other square matrix is just going to give you the same square matrix back. So like I times B is just B. And anytime you multiply a matrix with the identity matrix, actually this is a special case where the multiplication is commutative. So B times I also gives you B back, right? So it's only commutative in, well, not only, but there's special cases where matrix-matrix multiplication is commutative, but in general it's not. Like, what if we were to multiply A times B, we get this result. If we multiply instead B times A, you get a different result. So not always commutative. Like these two matrices do not commute, but the identity matrix does commute. It always gives you back the same matrix. So that's what makes it a little bit special. And, you know, for every real number, like for the number 7, we said that 1 is the identity because if you multiply by 1, you just get 7 back. Well, 7 has a reciprocal. And what's special about the reciprocal of 7 is that if you multiply 7 times its reciprocal, you get back the identity, right? So the reciprocal of 7 is 1/7, and every single real number has a reciprocal. So if you multiply a number times its reciprocal, you get back the identity. Some matrices, not all of them, but some matrices have what are called inverse matrices. And so if a matrix is invertible, then we use a little -1 up there to denote its inverse. And matrix multiplication of a matrix times its inverse is going to give you the identity matrix. And a matrix will commute with its own matrix inverse. So if I take the matrix A times its inverse, it will give me the identity function. If I take the inverse of the matrix A times the matrix A, it will also give me the identity function. So the question you might ask is, how do we find a matrix inverse? Like, if I tell you that the matrix B is the matrix 1, 2, 3, 4, and then I were to ask you, what is the matrix inverse? What's the 2 by 2 matrix where if I multiply that matrix times B, I get the identity matrix? How would you find that? One way to, and this is just a reminder, but if you wanted to solve the matrix vector equation, A, V equals B, we did Gaussian elimination on the augmented matrix, and so sometimes we write the augmented matrix as this, A augmented with B. And after doing Gaussian elimination, what we ended up with was the identity matrix augmented with your solution vector. I'll show you what I mean in case. I know this is a lot of information, so it's like easy to forget. But when we did Gaussian elimination on this system of equations, what we ended up with after Gaussian elimination was the 3 by 3 identity matrix augmented with my solution vector. Okay, so if that works as a way to solve matrix vector equations, then what if instead of having the vector x here, what if you replace the vector x with the matrix A inverse, you know? So instead of having AX equals B, now we have A times A inverse equals I. Well, just use this formula, but replace the B with an I, and then replace the X with A inverse. And what this tells us is if I make a little augmented matrix where I take my matrix A and augment it with the identity matrix, and then I do Gaussian elimination to it, I can get a new augmented matrix where it's the identity matrix augmented with my inverse matrix. Okay, so let's try that. I'm going to take my matrix A, 1, 2, 3, 4, and now I'm going to augment it with the 2 by 2 identity matrix. Okay? Now let's do Gaussian elimination, and the goal here, as stated right there, is that I'm going to have 1, 0, 0, 1, and then a 2 by 2 matrix that represents the inverse of A. So, I already have a 1 in the top left corner, which is nice. Now I want the 3 to be a 0. To make the 3 a 0, I'm going to subtract the first row from the second row 3 times. So 3 minus 3 times 1 is going to be 0. 4 minus 3 times 2 is going to be negative 2. 0 minus 3 times 1 is going to be negative 3. And then 1 minus 3 times 0 is going to be 1. The next thing I would like is I would like that 2, I want that positive 2 to be a 0 in the off diagonal. And in order to make that happen, I'm going to add the second row to the first row. Yeah. So 1 plus 0 is 1. 2 plus negative 2 is 0. 1 plus negative 3 is negative 2. And 0 plus 1 is 1. I'm really close now. The last thing I need to do is divide the second row by a negative 2. And if I divide the second row by negative 2, I'll get 3 halves and negative 1 half. So that means this 2 by 2 matrix has to be my identity, or sorry, the inverse matrix. Okay? Are we following? Cool. Let's check our work, and we're going to use Python. We're going to use this command we looked up earlier. It's going to be linearalgebra.inv for the matrix inverse. So first, I have to tell Python that my matrix A is 1, 2, 3, 4. And then I just have to say linear algebra.inv of A. And the answer, if we got it right, should be -2, 1, 1.5, and -0.5. Yeah, and so we got it right. That's our inverse matrix. And if I actually want to save what this inverse matrix is, I might name it something like A, I, and V, and then I can set it equal to that. So now I have it saved. And just to check, does this make sense? Let's do the matrix multiplication of A with its inverse. A times A inverse. So what is this matrix? We've got 1, 0, 1, but what is that on the off diagonal? It's 1.11 something, but that means times 10 to the power -16. So that's a super, super, super tiny number. That pops up because of round off error, because our computers can only hold a finite memory, and somehow round off error that happens ended up skewing this. So it's not a perfect identity matrix whenever you do the machine calculation, because you're introduced over the what we call machine error. You have to talk to like a computer scientist if you want to know about how a computer actually adds and subtracts things. But anyways, that is essentially 0. That is practically 0. And likewise, a matrix commutes with its inverse, so we can say A inverse times A, and also get the same thing with just a tiny little bit of round off error appearing there. Okay. Well, at this point, I'd say we are doing very good with how we are moving along. So let's do another example of trying to find a matrix inverse. Again, now the goal is to figure out what the inverse is. And how we're going to do it, we're going to start off by writing down the matrix, and then augmenting this with the identity matrix. And since my matrix is 3 by 3, we use the 3 by 3 identity matrix. Of course, the goal is that we will end up with an identity matrix augmented with the inverse matrix that we're looking for, which should be a 3 by 3 matrix. So, using Gaussian elimination, I've already got 1, 0, 0. First column is perfect. The second column, not super great. Actually, the first thing I'm thinking of in my own, personal bubble, I am looking at this one. I think we can get rid of this one easily because I could just subtract the third row. This one is a little bit more difficult to get rid of because if I were to subtract the second row, it's going to mess up that 0, and I don't want to mess up that 0. So let's first try to tackle that one right here. And we're going to do that by subtracting the third row from the second row. So first row remains the same in this step. And now we write the second row minus the third row. So 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 0 is 0. 0 minus 1 is -1. Okay. Third row remains the same. And now, to get my desired inverse matrix, I just have to take the first row and subtract the second row. Oops. 0 minus -1, that should actually be a positive one, right? Okay. So that means that this is my inverse matrix.
Correct.
That's correct? Okay. The way you do this with Python is you have to tell Python your matrix is 1, 1, 0. Oops, I need 2 square brackets. 1, 1, 0, 0, 1, 1, 0, 0, 1. And then we take linear algebra.inv of m, and we'll assign that to the variable minv, and then see what it is. Yeah, I think that's the same thing we got. And you'll notice that if you multiply the matrix times its inverse, then you get out the identity matrix. So perfect. Cool. So another thing I should say is that we can use matrix inverses to solve the matrix vector equation. Okay, so if you have the matrix vector equation AV equals B, and we want to solve for V, what I can do is look at this equation and multiply both sides by A inverse. But on the left side of my equation, what is A inverse times A? That's the identity matrix. Now, if we say that V is the vector xyz, and I is the identity matrix, a 3 by 3 identity matrix, then we're talking about the matrix one, with ones on the diagonal, times the vector xyz. This product is going to be the vector xyz, right? You take the dot product of 1x plus 0y plus 0z, and then the dot product 0x plus 1y plus 0z, and then the dot product 0x plus 0y plus 1z. And the identity matrix will also just return the same vector whenever you do matrix vector multiplication, multiplying by the identity matrix. Okay? And that means, going back here, the left side is just the vector v, and this is A inverse times b, and that means, v, that's the unknown we're solving for. And if we're solving for v, we're assuming that b is some known vector, right? And while we might not immediately know what A inverse is, we can find what A inverse is if we know what the matrix A is. So one way you could solve the matrix vector equation now is you could take the inverse of your matrix A, multiply that times B, and if you do matrix vector multiplication here, we can find out what V was. So let's try this in Python. And we'll try to come up with something nice here. So the matrix A is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. The vector B can just be, something a little bit creative. 1, 10, 100. And so I'm trying to solve the equation A times x equals b. What I could do is linear algebra dot solve A comma b, and it's going to tell me what my vector x should be. Oh, shoot. this is a whole thing. That's not a good solution, and let me tell you why. A moment ago, I said if a matrix is invertible, then it has an inverse, right? But this first statement is really important. If a matrix is invertible. Sometimes you can have a square matrix that does not have an inverse, okay? First of all, only square matrices are invertible. If it's rectangular in any shape, it doesn't have an inverse. But even square matrices are not invertible sometimes. And so, let me show you what I mean. Like the matrix 1, 2, 3, 4 is invertible. But this matrix 1, 2, 2, 4 is not, because the first column is equal to a scalar times the second column. What is that scalar? Do you know what scalar you multiply times the second column to get my first column?
The first times the first.
Yeah, in this equation, first column equals k times second column. What's k?
2.
So 2 times 2 would be 4, and 2 times 4 would be 8.
Yeah, whatever. It's half.
It's half. Yeah. If I put k on the other side of the equation, it would be 2. So your brain was on the right track. But yeah, k in this would be 1/2. And if one column is just a scalar multiple of another column, it turns out your matrix is not invertible. And there's a good explanation for this, but I know I can't explain the whole thing in the next 10 minutes. But that's a rule, is that if one column is a scalar multiple of another, then it's no good. So the matrix that I just put into Python was this one. I made the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. It turns out this matrix is not, because the first column plus the second column is equal to the third column. And that also makes a matrix not invertible. And I know that this sounds like a bunch of crazy rules, but basically what you're saying is if you take each of your columns as being a vector itself, you can't have vectors that are parallel to each other, and you can't have vectors that add to equal each other. The most proper way of saying this is that one of your columns cannot be a linear combination of the other columns. I think maybe we have time to explain why this happens. I just need a little bit of space to write, and then I can show you why. So what always happens is we want to find the inverse. So of course we augment that with the identity matrix. And then we're going to do row operations until the left side is the identity matrix and the right side is the inverse matrix, right? So I've already got the 1 where I want that to be. Maybe the next thing I do is I want the 4 to be a 0 And I can make the 4 a 0 by subtracting the first row from the second row 4 times, right? So 4 minus 4 times 1 would be 0. 5 minus 4 times 2 would be 5 minus 8, which would be negative 3. 6 minus 4 times 3 is 6 minus 12, which is negative 6. 0 minus 4 times 1 is negative 4. 1 minus 4 times 0 is 1. 0 minus 4 times 0 is 0. Okay. Then I also want the 7 to be a 0. And so I'll subtract 7 times the first row from the third row. And so 7 minus 7 times 1 is 0. 8 minus 7 times 2 is negative 6. 9 minus 7 times 3 is negative 12.
Yes.
0 minus 7 times 1 is negative 7, and then 0, 1. Okay. Then I also want this negative 6 to be a 0. And so what I'll do is I'll subtract 2 times the second row from the third row, so I can make this negative 6 into a 0. And if I do third row minus 2 times the second row, so 0 minus 2 times 0 is 0. Negative 6 minus 2 times negative 3 is also a 0 like I want, but then negative 12 minus 2 times negative 6 is 0. Negative 7 minus 2 times negative 4 is going to be 1. Negative 2 and 1. Okay. But then we get here, and we can make the negative 3 into a 1 by dividing the second row by negative 3, and it's a 1. But you're never going to be able to finish this Gaussian elimination problem because you need this entry to be a 1. But, anytime you try to put something back into this entry right here, you'll end up introducing something to this entry or to that entry. And play with it all you want, but it just doesn't work. There's no way to make these 9 entries over here into the identity matrix. And that happens every single time you can write one of the columns of your matrix as a linear combination of the other two. So if you're wondering why I got a really strange answer here in Python, that's the whole explanation, is that we cannot solve this matrix vector equation because you can't even take the inverse of A. So what if I tell Python, take the inverse of my matrix A? It's going to try to do this, and it's going to come up with an answer. But if you look at the 10 to the power 15 on all the entries, it's blown up to be like a huge freaking entry. These all are just generated by machine rounding error, machine error. They're not actually anything mathematical. So what do we do instead? We have to come up with a better matrix. We'll call it the matrix 1, 2, 3, 4, 5, 6. And then as long as it's not like 7, 8, 9, it's going to work. So like maybe we try like 7, 8, 8. Maybe it was. And then now if we want to solve this equation, we can actually solve it. Because my columns are independent of each other. And we get an answer that makes sense. So that's one way to solve it. Whenever I use this command in Python, what Python is doing behind the scenes is it's doing Gaussian elimination to the augmented matrix A augmented with B, like we did at the very beginning of class. What I was just explaining a moment ago is that there's another way to solve this, which is to say, take the inverse of A, multiply that with B, and that should give you the same solution. So let's try that. let's take the inverse of A, like that. And then we're going to multiply that A inverse times B with that command. So notice, whether I solve this using Gaussian elimination or I solve it by first taking the inverse and then using matrix multiplication, those two solutions are the same.